And our next speaker and the last presenter for this session is Thomas Weibler, as you clearly can see on the color scheme from Flex Optics. And his focus is on creativity, innovation driven by real-life customer problems. And today he will show us how to keep our DWDM infrastructure future-proof for the 1.6 terabit world. And I've been told this is a completely new presentation, so enjoy.
Thank you very much, Franziska. You might already had, I'm pretty sure you had that experience. You have a really great conversation with someone you know, and you do a really deep technical dive, and then after that conversation you think, hey, what is so special on this certain technology, or why is this happening? I'm Thomas Weibler, co-founder and CTO at Flex Optics, and I was actually that one having a conversation at the last actually not last ROADM, but at the RIPE meeting in Lisbon with Blake Willis. Some of you might know Blake Willis, so when you have a conversation with him, it might get some intense, or it's very intense, the conversation, but it was great. And the topic we were talking about was mainly about DWDM networks in large scale and also on high data rates starting from 400 gig with coherent modules, or coherent technology in general. And while we were talking, there were some key wordings always used. There was this balanced receiver mentioned quite often, and also the colorless thing. And then I got back to the company, had a conversation internally with some folks, one of our hardware developers got, and it turned out to be a real brain fuck. And that's the talk about. So I want to show you what we did and achieved, and why it is so complicated, and to give you a little bit more innards about the balanced receivers and colorless. So, but let's start easy first. Lasers. Lasers have been around for a long period of time, started in the 60s, but those lasers were not usable for us in the telecommunication industry. They were big, they were power hungry, and they needed a lot of cooling, especially with liquid nitrogen or something like this. And in the 1970s, the first semiconductor lasers were really helpful and usable for us running at room temperature and small size. And when we focus on them now, so what has been involved since the 70s, it looks a little bit like this. So up there we have the typical unmodulated line width of a LED. So you have a center frequency or a center wavelength of 1300 nanometers and an unmodulated line with this nice bell curve with a rough width of 100 nanometers. So it's quite broad. When we get up here to the Fabry-Perot laser, which is mainly used in 1 gig technology or data rate, this is getting really a little bit more narrow, 10 nanometers only, and it was very characteristic with those two side peaks next to the center wavelength. And then the interesting part is now getting there. On the green section, distributed feedback lasers, we're getting closer, just 1 nanometer of the width of the peak now, and I also show here it with 125 gigahertz, so we change it from the wavelengths to the frequency now. And the most latest development here on the red one, on the red side, are the external cavity lasers, which are used for coherent modules and have a really narrow line width of 1 megahertz only. So why was coherent not pushed earlier out into the field is a tricky question. But first of all, let's look what we need to do a transmission in general for coherent. For sure, we need some compute power to do all the compute for the higher order modulation to get bits and bytes out instead of having this constellation thingy where I come later on. The other thing is you need a precise laser there for your optical carrier, and you need an amplification as well to reach longer distance, and the signal itself gets disturbed while it's traversing on the fiber. The velocity of different frequencies changes, and you need a compensation of the dispersion. Now for coherent, the EDFA or the amplification and the dispersion compensation fiber was around, but we were lacking precisely lasers, and especially we were lacking DSPs to do all the math and the calculation. It has been done in the past, but not in real time. It was offloaded to big number crunching computers. They got the data from the analog digital converter. They did their math, returned a result, but this was not in line rate actually. This was offloaded. So what else can we do? When we want to increase the traffic per fiber, in general, in the top one here, we have our optical carrier, and the optical bandwidth itself, which carries all the information content we want to move forward or to our receiver, is in this curve as well encoded, or that's the information content. You have two choices. The first one is, and I'm pretty sure all of you are using this, you use WDM technology, either C or DWDM, it doesn't matter, and you have different colors on your fiber. And you separate them with filters. And the interesting part here is, well, you lose some spectrum between the filters because they have to separate the channels with each other. On the other side, with the solution 2, well, what you can do is basically fed in way more information into one channel, into one carrier, and make it broader. So you increase the frequency of one carrier, and you fed in more information there. Well, this was not really a brain fuck. Actually, it started now with the complex numbers. On-off keying is broadly used for 10 gig and 100 gig in a direct detection manner. So how does this look like? In the middle, there is our detector. That's the center one, the most important one. But first of all, face here on the left side. We do have our signal coming on the fiber, and either the phase or the frequency is continuous, or the phase does change, or even the frequency does change. In a coherent world, all happens to the same time. Polarization is a little bit out there because I will come to that one later. And it's going to hit the receiver. The receiver is a diode, a photodetector. And it works pretty simple. When there is light on the photodetector, current goes through, you get a 1. If there is no light on the photodetector, it's a 0 because no current is flowing. But for that photodetector, everything looks the same. It doesn't matter if the phase does change or the frequency. So the resulting digital signal, the 0 and 1, looks like this. It's all the same. And you are using this every day when you operate bidirectional transceivers, because they make use of this effect because the frequency is different on a bidirectional. Now, a little bit back to my talk 2 years ago about coherent modulation, 16 QAM I introduced there. I don't want to go into details now, but we introduced the constellation diagram with those 16 dots. The great thing is, we have those 16 dots, we can encode 4 bits per symbol, and this increases our data rate tremendously without increasing the baud rate that much. But looking now a little bit more precise on those dots, and when we focus on one dot especially, how do we actually in that space locate that dot? There are 2 ways. There's the blue way. Either you have the amplitude, it's a vector, so a vector has directions, and this vector also has an angle, the argument. With those 2 variables, you can position that dot precisely. The other way is you use the x and the y component, or also what we call it the quadrature, the q component, and the in-phase component, the I component. And for later on, we're going to focus more on the in-phase component. This is pretty simple geometry. Just do the calculation. Yeah. What I said at the beginning was about this receiver. So it seems like the coherent receiver is quite important. And let's focus a little bit more on the receiver side now. And in the middle of, when we look at the first one as a single-ended receiver, there is this coupler. The coupler is not an LC duplex coupler. It's more, the coupler is based like you have two fibers not touching each other but very close to each other with two interfaces or in fibers and two out fibers. And when we connect them to our detector, what happens is on the interfaces on those two, we have two signals coming in. The first one is our carrier, the optical carrier, the orange one up there, with the optical bandwidth, with the actual content. And on the second one, we do have a local oscillator. The great thing is the local oscillator is taking from the transmitter of the same transceiver. It's operating almost on the same frequency. And you combine it in the coupler. And within the coupler, some effects do happening, but they end up together on one leg of that coupler, and it hits the diode. And we get a signal, and the great thing is, because of that coupler, when you combine the local oscillator with the optical carrier, you can detect the optical carrier that's happening, and we have a down-converted signal on a lower frequency. I will come to that later. The second one is, and now this balance is coming into place, on the incoming interfaces, it looks all the same. But on the outgoing, it looks a little bit different. We have now, instead of one detector, we have two of them. They both detect the signal here. Orange and green, green and orange. But the coupler has another effect. What the coupler does, it does a phase change for the cross port. So the cross port for the orange signal is down there. So this phase is changed by 90 degrees. And the same applies to the local oscillator, the green signal. On the cross port, the phase is also changed. And now back to high school. When you do have a phase change, you have waves. And when you have two waves, they are at the same level and they overlap. What's going to happen? They get more gain. They amplify themselves. They are higher. So you get more output, basically. On the other side, you get less noise, because also what they do is, on the noise level, it eliminates in itself. And that's pretty awesome. And so our down-converted signal over there has a way higher amplitude and less noise. So far for the general detection, but now we have the phase. How do we get out the phase? Well, we need one balanced detector for the I component, and we need one balanced detector for the Q component. We combine them, and the local oscillator is not fed directly to the coupler any longer. No, we also split the signal of the local oscillator, like we do it with the signal. We phase shift it again for the lower part, for the Q part, by 90 degrees. And within the coupler, we do again, for the cross ports, the phase shift. And hooray, we have now two balanced detectors, but they are phase diverse then. We get the I and the Q component, and we can really precisely define the point in the constellation diagram where it belongs to, because we have I and Q now. And when it's not so, this is already somehow complicated. We add a little bit more complexity there. Instead of having two of those balanced receivers, we have four now, because we have two polarizations. And again, in front, the signal is split with the beam, polarization beam splitter into two polarizations. Local oscillator again, same setup. And inside now, it's not only one coupler, it's a cascade of couplers and splitters, tiny semiconductor components, and they are hitting each of them the I and Q component for the phase, and it does do it for the polarization 2. And also for the polarization 1 up there. Somehow difficult, and it looks a little bit like rocket science to build this, but there is even more. As I said, we have this down-converted signal at the beginning. And we get rid of the local oscillator together with, or we get rid of the optical carrier together with the local oscillator, but there are different ways to do it. And the first one on the top you see, it's called heterodyne. So what happens there is we have the local oscillator running at a frequency at, let's say, 192.8 8 terahertz for simplification, and the optical carrier is a little bit offsetted by roughly 622 gigahertz. So the difference between those two carriers, or the oscillator and the carrier, is called the intermediate frequency. And the drawback is what happens in that coupler is, well, we also get a mirror frequency, which we actually don't want, because we have an upper part and a lower part, but we don't want that lower frequency, the mirror frequency, because on the mirror frequency there could be another channel, and they would interfere with each other, and we don't want that. So what happens, it's down converted, and the intermediate frequency is at 600 gigahertz. And all the folks who are doing electronics, building a detector doing 600 gigahertz, it's possible somehow, but it's really a challenge to get there. So that's not really a solution. So the alternative, you can even see it now, is the homodynamic solution. Well, just do it simple, bring the local oscillator to the exact frequency of the optic carrier. Technology-wise, this is doable. The great thing is we don't have a mirror frequency any longer because they are overlapping each other, and you get a perfect intermediate frequency of 0 gigahertz, and running at 0 gigahertz is great, quite easy. The problem is it's technical-wise quite difficult to build and complex, and when it's complex, it's getting big and it costs money. You can do this with an OPLL, but nothing which you can place into a transceiver. So the solution is the combination of both, called intradyne detection. What we do there is we bring the local oscillator as close as possible to the optical carrier, but not overlapping. And the local oscillator can be within that range of our 75 gigahertz, for example, in this scenario for a 400 gig signal. So 37.5 gigahertz to the positive, and also 37.5 gigahertz to the negative side. Within that range, the local oscillator needs to be placed, and then the mirror frequency is not an issue any longer because it's within our carrier, within our frequency where we want to be. And then we don't disturb other channels next to each other. And hooray, the great thing is also our intermediate frequency is at 5 gigahertz. And 5 gigahertz is something you can really easily detect when you lock your detector to that frequency. And this is also the important part on the colorless thing, because now you can really filter only this spectrum or this frequency for the receiver. In other words, the receiver only sees what he wants to see, and this is not driven by a physical filter, no, it's driven by the characteristics of his own operation frequency. About some numbers, when you look at a 400 gig, it's roughly running with 60 gigabaud. You need a detector doing 35 gigahertz, and for 800 gigabit, it's a little bit higher. We are running at 70 gigahertz then. Yeah, so we almost made it. It looks like we are launching and getting to the moon, but there's a little bit more, and when we get to the moon, there is even a universe. And now let's look into that universe, what we can do with these characteristics for coherent detection, basically. So as I already said, there are different speeds out there, starting from 400 gig up to 1.6 terabit, and the way they get more information into our band is they increase the frequency, the overall frequency. So at 1.6 terabit, we will end up, we need 300 gigahertz of a channel in the spectrum. You can combine them all together on the lower part here. Within, and you can imagine, this is a filter with 3 channels basically. You can combine them all within one filter. And when we do the math and build something like this, we will end up with a 400 gigahertz filter. Because when you only look at a 200 gigahertz filter, the 400 gig and 800 gig would still fit in there, but the 1.6 terabit won't fit in there any longer. So you need something broader than 200 gigahertz. And why are we focusing on 400 gigahertz? That's the important thing on the commercial off the shelf. For sure, you could also stick to a 300 gigahertz filter to fit everything into this filter block. But the 400 gigahertz is currently off the shelf available. It's no special deal to build them. And in comparison, what we have done in the past we were running tons of channels, up to 96 with nice slices of 50 gigahertz, but we lost also a lot of spectrum between the filters of each other. And a great benefit as well is when you look at the specs of such a filter doing 12 channels with 400 gigahertz, every channel is carrying 1.6 terabit, do the math, you can do there up to 15 terabits on your fiber. And also for the optics folks, if they have longer spans, well, attenuation and insertion loss is a critical thing. And typically we are there at 2 dB only for a 12 channel multiplexer, while looking back to those days to running a 40 channel 100 gigahertz AWG, they are roughly at 6-7 dB insertion loss per channel, depending how they are distributed. So that's a really great benefit when we focus just on those 2 channels, 12 channels, sorry. Because we can also do interesting things now. We could cascade in there still 8 channels 50 gigahertz, on-off keying 10 gigabit, legacy equipment, or build your own super channel. Because instead of just fading in there one carrier doing 1.6 terabit, you could also fade in 4 carriers doing each 400 gigabit and use a simple splitter on the out interface and distribute the signal to all receivers and let the receiver decide which signal is intended for him. It would look like this then. So the upper part has been built so far, because this is our mixed signal going to the upper part, but the lower one, the coherent module, or the blue one, only takes the blue curve, because our receiver is locked to that frequency and tuned to that frequency, and now we get a benefit out there. It can see all the waves, but it doesn't matter, or all the 3 out of frequency, but it doesn't matter. It just discards them and takes the blue one, and the same does the green, the yellow, and the coherent. When I did the first dry run of that talk in the company, one of my engineers said, hey, yeah, that's cool, but this is going to be getting a little bit messy, because typically on the multiplexers you have all those ports. They are numbered, and now when you have a splitter, well, you don't know what's actually at the end of that of that 4 splitter leaves. Basically everything gets to those 4 transceivers. He was right. So the answer is, yeah, you need a frequency plan if you want to do something like this. So you become your own BNetzA or Bundesnetzagentur to know, okay, that's a kind of a shared media, and we should know on which leg of the splitter is which transceiver or which frequency connected. This is pretty awesome in my point of view, just making the fact that it's colorless, and we have this, in the past this broad receiver was used for bidirectionals as a benefit, that it took all the light. Now we do it the other way around. We say, hey, we only want to lock to a certain frequency and can even filter on the detector level without filtering on the optical side, which is pretty gorgeous. For myself, I'm really looking forward to the social tonight, because getting all there was really a brain fuck. And yeah, I'm happy to take questions and see you also later at the social. Thank you very much.
Thank you, Thomas. And we actually have time for questions. Do we have questions? Please wave so I can see you. Okay, I think everyone is just very eager for the closing and to go to the social. But thank you again. We know where to find you.
Thank you.